गुड मॉर्निंग सर, आवाज आ रही है सर?
यस सर, आवाज आ रही है सर आपकी।
So, good morning to all esteemed guests, respected speaker, faculty members, and participants. It is an honor and a privilege to welcome you all for this FTP on opportunity and challenges in modern power system, day 2 morning session. University since 2021. He earned 95 publications between 2010 and 25, including 7 journal articles, book chapters, several books, conference proceeding. His scholarly impact is wonderful, uh, further highlighted by 708 citations and H index of 15. Notably, he received the Best Paper Award at Spinger Nature's third International Conference on Renewable Power and has been consistently placed among the top 2% of researchers in this world by Stanford University, USA in 21, 22, 2023, and 24. Additionally, he was honored with the Best Associate Editor Award by the Journal of Electrical Engineering and Technology in 2021, 2022, and 23. We will take a session on topic opportunities and challenges in modern power system frequency control. I encourage all the participants to actively engage and ask questions after the session. Without further delay, let us welcome Dr. Arya, sir, to begin this session. Sir, please
Okay
proceed.
sir, thank you very much sir. Yes sir, my screen is visible to all of you. Please
Yes, yes.
confirm. Okay, thank you sir. Okay sir. So, so the topic is opportunities and challenges in modern power system frequency control. So it is very important to maintain the frequency of power system at the scheduled value. Otherwise, we can face blackouts in power systems. So it is very important to maintain the frequency at or nearly around 50 hertz, specifically in India, and in some countries this value is 60 hertz. So first we will check some basic topics about the power system. So content of the talk will include electric power system block diagram. Then we will discuss about the evolution of national grid. Then we will talk about the total installed capacity. Then we will take overview of HVDC transmission system. Then we will come to the electric power generation system, and in the last I will show few simulation results on power system frequency control. So all of you know that there is a generation, transmission, and distribution. So takes place. So actually, we have alternators which produce electricity normally at 11 kV or 33 kV. So to transmit this power, which is generated at 11 kV or 33 kV, should be step up to reduce the losses. So the transmission levels which are used in India, they are 132 kV, 220 kV, 400 kV, or 765 kV. So we transmit power at these levels as per the distance. So if the distance is less, we can use low voltage levels. If the distance is long, we must use higher voltage levels to reduce the losses during the transmission of the power from the generators to the load side. So now there may be various types of consumers. Some big, very large consumers actually use higher voltages. So we have to transmit power to those large consumers at very higher voltages. These higher voltages may be 132 kV or 220 kV, and it may be 400 kV. Or then there may be some consumers which less power. So there, in that case, is the transmission power may be transmission of the power may be taken place at 66 kV or 33 kV. So, but at the load end or the normal consumers, we use uh, transmission or distribution. We will actually distribute power. Sometimes we say that the primary distribution at 33 kV or 11 kV, but at last, because the distance is very less, so at the consumer level, we are using the voltage at 230 volt or 400 volt. So we actually use distribution transformers at this level. To step up, we will use the power transformers, and at distribution level, we use distribution transformers which change power from 11 kV to 0.23 or 0.4 kV, or 33 kV to 0.4 or 0.23 kV. So all the consumers use power at these levels. So all the appliances in the electrical engineering, electrical appliances, they use single phase power or three phase powers. So the transformers are essentials to step down these voltages to the usable voltage of 0.3 kV or 0.23 kV. So it is the general uh, block diagram how transmission takes place, and then it is how generation takes place, and then this power is transmitted, and then this power is distributed over a less distance. So and how we can use this power at 0.3 or uh, 0.4 or 0.23 kV. So in India, the maximum voltage which is used for transmission is 765 kV. But normally the share of the 400 kV is prevalent. Yes, please, please. Yes, yes. So there are few transmission lines which have the voltage level of 765 kV. So there are many transmission lines available in India. Some of these are given here. So the first 765 kV transmission line was started in 2007 in India. So it was the NTPC projects at the CPET Bilaspur. So as of March 31, 2024, India's power transmission network more than 220 kV or higher that stood at 485,544 kilometers, and out of which 765 kV lines are 54,797 kilometers, means it has a share of about 11%. Means most of the share goes to the 400 kV or 220 kV transmission lines. Now, there is also a process going on to inaugurate our 1200 kV transmission line. So, between Varda and Aurangabad, a 1200 kV overhead line having a length of 696 kilometer. Its work is going on, and the project is currently under construction, and it was expected to be commissioned in 2021, but still it is under construction. Now, why advantages of high voltage transmission lines? So already we know that if we will increase the voltage level for a specific power, then the current level will reduce. And so if the current level reduce, means copper losses will also reduce. So the main objective of increasing the voltage level is to reduce the copper losses, so that without any power loss we can transmit power from one place to other place. So this is an example. It is given here that if we have 200 megawatt of power to be transmitted at 11 kV and consider power factor 0.8, in this case the amount of current that will flow through the line will be 13,122 ampere. But if we will transmit the same power
अब देखो
at
माइक्रोवेव के अनुप्रयोग कहाँ
Manish,
कहाँ है
Manish Dubey,
ठीक है
please mute your phone, your mic.
कहाँ कहाँ है माइक्रोवेव के अनुप्रयोग देखो तो अगर देखोगी तो पॉइंट टू पॉइंट
Yes.
कम्युनिकेशन में
Yes, Manish Dubey ji. Yes, if we will increase the voltage level from 11 kV to 220 kV and same power factor, then this current will reduce from 13,000 to only 656 ampere. In this way, we can reduce a large power loss in terms of I square R losses or heat losses. So also we can reduce the conductor size, and we can also save the cost if we will increase the voltage level. So it is very, very important to transmit power from one place to other place at higher voltages. Now economic choice of the transmission voltage. So transmission of the electricity at higher voltage is very, very efficient. It makes the saving in the conductor material. Also, it improves the voltage regulation. Okay, because if current is reduced, means voltage drops also reduced. So if voltage drop reduced, means voltage regulation will improve. So limitations of high transmission lines, what may be the limitations? So if we will increase the voltage levels, so cost of insulators will increase, and cost of transformers will increase, then cost of switch gear will increase, cost of lightning arresters will increase, cost of support towers will increase. We will require taller towers with longer cross arms. So for overall economy, there should be a optimum transmission voltage. So this limit uh, uh, may be reached when the saving in the cost of conductor is offset by the increased cost of transformers. Because we are saving the copper, but also there is the increased cost of insulator transformers of switch gears. So we should also check whether we are getting benefited by increasing the voltage levels or not. So we should check the economic transmission voltage. So economic transmission voltage may be one for which the sum of cost of conductor material, transformers, switch gears, insulators, and other equipments will be minimum. So it is very important. Now, now there are 5 regions. So power grid has 5 regions. So there already you know that there are eastern region, then there is a western region, then there is a northern region, then there is a southern region and northeastern regions. So previously they were working in isolated mode, but in current scenario they are all interconnected with each other.
क्लास भी कैंसिल कर दिया है इसलिए
They are interconnected with
सर अटेंडेंस कितनी
1 minute, please. There is some 1 minute, please.
Ankita, mute yourself.
Yes, yes. Yes, so in 1991, northern and north, northern eastern and eastern regions were these grids were connected. This eastern and northeastern region, these grids were connected, and then this western region was connected in 2003. Okay. Then in August 2006, northern and eastern grids were connected. Thereby, 4 regional grids are synchronously connected, forming a central grid. So then this was a they were interconnected with each other. Then there is a this northern eastern in 2016 this northern grid was connected, and in 2013 this southern grid was also interconnected. So as 31st December 2013, the southern grid was connected to the central grid. So from this date there was a one nation, one grid and one frequency. This phenomenon taken place in on the date of 31st December 2013. So there are various benefits of interconnecting these grids with each other, but there may be some difficulties if the frequency or blackouts taken place in one area, then that blackouts may also affect other areas because all over India is interconnected. currently. So, but the benefit is that we can transmit power from one grid to other grid because all our grids are interconnected. So we can assist the other grid. If there is a power requirement, we can transmit power from one grid to other grid. So it is, there are some benefits, more benefits and less disadvantages. But currently we have efficient control mechanism, efficient protection mechanism. So the chances of blackouts are very minimal. So the interconnection of all these grids is very, very beneficial for the Indian scenario. Now, the installed capacity currently, as of there is some problem in my screen. Yes, yes. So the is my screen visible? Yes,
Yes, sir,
please.
you are visible, sir.
Okay, okay. So the installed capacity as on 31st Jan 2025. So the installed capacity is 466 gigawatt in India. And in this 466 gigawatt, nuclear portion is 8.8 gigawatt, then hydro is 46.97 gigawatt, then small hydro 1 gigawatt, pumped hydro 4.75, wind 48.37 gigawatt, and solar is more than now gigawatt, and coal is 220 gigawatt, oil and gas 25, and biopower 11.4 gigawatt. So actually, in current scenario, we are focusing on renewable energy sources, and we have current renewable energy sources equal to 1,65,200, around 200 gigawatt, megawatt. So our target for 2030 is 500 gigawatt only from the RES, renewable energy sources. So in renewable energy sources, there are small hydro plants, they are covered in renewable energy sources, then wind power plant and bio power plants and solar power plants. So big hydro power plants are not considered in the renewable sources of energy because they impact the environment adversely. They also impact the population. So we consider big hydro power plants in conventional power plants, but small
भाई
power plants
नहीं
are
है अभी क्या
considered.
नाम से फीडबैक
Then, so leading countries in electricity generation worldwide. So China is the leading country in electric power generation. Then there is a United States. Then we come at the third position. We are generating such uh, amount of power. And then Russia, because population of India is large, we are generating more power and we stood at third position. But we are not consuming such power per capita. So the share of community power capacity by technology 2010 to 2027. So it is a trend that coal portion is reducing over the year. You can see that the coal, the power generation from the coal is reducing year by year. No new power plant based on the coal are established or installed currently. Actually, the portion of the wind is also increasing, and there is a drastic increase in the solar PV power. Hydropower plants proportion is also decreasing over the years, but and bioenergy, there is no significant change in bioenergy, but main focus in current scenario is on the wind and solar power. Also in India, we are mainly focusing on these two, wind and solar. Now, thermal power plants in India, we have Vindhyachal thermal power plants at Madhya Pradesh, and it is the biggest thermal power plant in India. Its capacity is 760 megawatt. Then we have a Mundra thermal power station in Gujarat. Its capacity is 4,620 megawatt. Also, we have Rian thermal power plant. Its capacity is 3,000 megawatt. So, if we compare with the world, there is a thermal power plant whose capacity is 6,720 megawatt in China. And there is another power plant whose capacity is 6,100. It is situated in South Korea. So if we compare, the highest capacity of India is 4,700. So our thermal power plant capacity is not uh, up to the is not equal to the other power plants, thermal power plants in other world. So we have to increase this capacity. Now, top five solar countries in the world. So China is at number one. So it is the 2023 data. Then there is
ऑन हो
a
गया था, स्टार्टिंग में बंद हो
USA,
गया। अब
USA,
स्लाइड नहीं आई जब तक नहीं होगा।
yes, then USA, then Japan, then Germany and India. We stood at fifth position, but in 2025, we have came at fourth position because we have dedicatedly increased our solar production in India. So government is encouraging the uh, companies and also encouraging the population to set up the solar power plant at their rooftop. So there is a one PM Surya Ghar Muft Bijli Yojana. So government is giving subsidy. So subsidy may be up to 78,000 for 3 kilowatt and 60,000 for 2 kilowatt and 30,000 for 1 kilowatt system. So we are our proportion from the solar is increasing year by year. There is also PM Kisan Urja Suraksha Evam Uthan Mahabhiyan, PM Kusum scheme for the farmers. So government is giving subsidy, so we are increasing our power from the solar side. Also at every location or in India, there is a availability of the sun rays is large in India. But for the wind case, we are not doing well in comparison to the world. Again, at the top is China in wind power plant 329 gigawatt, then United States, then Germany, and then India. So in wind and solar, we stood at fourth number. So we have to increase this position. Now hydropower plants. So we have various hydropower plants. So there is a Tihri hydropower plants, Uttarakhand, 24 megawatt. Then Koyna hydroelectric power plants, 1960 megawatt. Then Sri Sailam hydropower plant. So this Tihri power plants is the biggest in terms of megawatt. And if we compare with the world, so there is a three George dams whose generation capacity 22,500 megawatt. Then there is other power plant 16,000 megawatt in China, and there is 14,000 megawatt power plant in the border of the Brazil and Paraguay. So main power plants in terms of hydro, they are also in the China. And now if we will come to the wind power plant, so in India there is a Bhupandal wind farm 1500 megawatt, Tamil Nadu. Then is Jaisalmer wind park, it is 1000, around 1000 megawatt. So, but in if we compare with the world, so the here there is around 8,000 megawatt power plant at China. So we are far before the China. Now, if we will come nuclear side, so presently India has 22 nuclear power reactors in 7 states, and installed capacity is around 8,000 megawatt. So there is a Kudankulam nuclear power plant. It was started in 2013, 2000 megawatt. Then Tarapur 1400 megawatt. Then Rajasthan atomic power plant, it is 1180 megawatt. And if you will compare with the world, then there is a nuclear power plant in Japan whose capacity is around 8,000 megawatt. So we also like in the nuclear power. Then solar, in case of solar, we have Badla Solar Park. It was started in 2018. So it is the power capacity is 2,245 megawatt. And there is another Pavagada solar power plant in Karnataka, 2000 megawatt. Then Kurnool ultra mega power plant, its capacity is 1000 megawatt. But if we will compare with China, its capacity is 15,730 megawatt. So China is leading in all sectors. Now, gross electricity consumptions per capita in financial year 2023 was 1,327 kilowatt per unit per capita. So, and we discussed that we stood in power generation at third place. But we can see that in this list, India is not visible, because our per capita energy consumption is very less. We have 140 crore people, and if we will divide total power generation, our per capita is very, very less. China per capita is good because they have higher power generation. So we have to think about it. We have to increase the power generation in India. Then come to the power transmission capabilities of various levels. So if we will compare 400 kV, 765 kV and 1200 kV lines, we can see that the ROW means right of way, that area taken by the tower. So in 400 kV, it is around 46 meter ROW, and for 765 kV it is 64 meter, and for 1200 kV it is 92 meter. Means if we will increase the voltage level, we have to increase the size of the tower. So it will take more land, and but capacity will increase if we will increase the voltage levels. So for 400 kV line, the transfer capacity is 600 to 700 megawatt, and it is increased to 2500 to 3000 megawatt for 765 kV, and it is increased to 600 to 8000 megawatt, 6000 megawatt to 8000 megawatt for 1200 kV. So if we will increase the voltage levels, we can transmit more power over the same line. So it is very important to increase the voltage levels. However, they will require more land. So the power in the below table, so the megawatt per meter per meter, uh, uh, how much megawatt can be transmitted over the transmission line. For 400 kV transmission line, we can transmit 22 megawatt per meter, and for 765 kV transmission line, we can send power at higher power around 45 megawatt per meter. Then if we will use plus minus 500 kV HVDC, so that we can transmit power around 48 megawatt per meter, and if we will use 1200 kV AC, we can transmit power 87 megawatt per meter. But if we will use the 800 kV HVDC, we can transmit power equal to 90 megawatt per meter. So we can see that for 1200 kV AC, we are power transfer capability is 87, but for 800 kV HVDC, the power transfer capability is slightly higher. So the power transfer capability of HVDC is higher in comparison to AC. So in current scenario, we are focusing on the HVDC transmission systems. So HVDC transmission systems, they can transmit power, more power or bulk power. They also assist the existing AC system. So for frequency control, this if we will have a HVDC system in parallel with the AC system, it will also assist the frequency of the system, or it will increase the security of the system. So the existence of the HVDC systems in transmission system, so it is essential for the security point of view. Also, it increase the power transfer capability of the existing system. So for HVDC, there is a generating station, then there is a switch yard, then we will use step up transformer, then we will use converting station. This converting station will convert AC into DC. Then we will use HVDC transmission line. We will again use inverting stations. It will convert DC into AC. And then we will use step down transformer, and we can use this step down power. So what is the important thing is that in HVDC we have to use converting stations to convert AC into DC and then DC into AC. But it will increase the cost. But by using these converting stations, we can handle the power flow over the HVDC transmission highly effectively. So these HVDC systems are very important to transmit power over longer distances. So we can see that the advantages and disadvantages of the HVDC and DC systems. So number of conductors in HVDC systems, they are less. We can use only 2 conductors in HVDC, and we have to use at least 3 in HVAC. So the suitability, the HVAC systems, they are suitable for distance less than 600 kilometers. But for longer distances, we should prefer HVDCs. If we want to transmit power at a distance more than 600 kilometers, so HVDC system will be highly economical. Now coronal loss is so in HVAC coronal loss are more and in HVDC they are less. So skin effect and Ferrant effect. So due to uneven current density, there is a skin effect in HVDC, Ferrant effect present in HVAC system. But these two effects, which are very important effects in HVAC, they are absent in HVDC systems. Now, conductor diameter. So it requires a conductor diameter of large value due to skin effect because in AC more of the current lies in the skin of the conductor and the in between the center there is no current, but in HVDC the whole volume is consumed for the current. Right of way, so right of way is also less, means we will require less land for the HVDC system. So tower size that will also less in HVDC. So there are many important advantages of using HVDC systems in comparison to HVAC systems. And yes, we can see that the power transfer capability over the distance is in HVDC that is constant, but if you will increase the distance, the power transfer capability that reduces in case of AC. And we can also connect two regions having different frequencies using HVDC link. If we want to purchase power from a other country whose frequency is not matched with us, so we can purchase power from that country by using this HVDC link. It can convert AC into DC, and when we will convert DC into AC, we can choose the required frequency. We can see that the transmission towers, so the in the HVAC transmission tower is very big and HVDC transmission is very small, or we can say that the area required or land required by the HVDC transmission is less. Now we can, if we will plot the cost versus distance plot, so for lower distances the HVAC is economical, but for higher distance, if we want to transmit power at longer distances, we can see from this curve that the DC is more economical, and there is a break even distance, or so this break even distance may be 500 to 600 kilometer of the transmission line, and this distance may be 40 to 50 kilometer in case of cables. So for longer distance, this HVDC transmission is economical. So the first HVDC link in India was commissioned in 1989, and it is not in use currently. It was discontinued in 2014. So we have various HVDC links, just like Rihand, Delhi, thus northeast to Agra. So we have various HVDC links, and the number of HVDC links is increasing year by year. So there is wind generators. Wind generators may be vertical axis or horizontal axis. So both these configurations are used, but mostly horizontal axis. So, and there may be another type of the wind power plants. There is offshore and onshore wind power plants. And this is the wind zone in India. We can see that the availability of the wind is not present in all the states of the country. So, its existence is limited. For wind power plants, there is a required a minimum speed of the wind, just like 3 meters per second. So, if this wind is available, we can install the wind power plant. Otherwise, we cannot install the wind power plant. So we have limited resources of the wind, but we are not extracting it our capability fully. So we should work in this way also. But in case of solar, in most of the regions of the India, we have uh, this power in plenty. Now come to the schematic arrangement of the steam power plant. So all of us know that this schematic power system arrangement in case of steam power plant. So we use actually coil in thermal power plants. So this coil is used to generate the steam, and the steam is used to rotate the turbine, and this turbine rotates the alternator, and this alternator actually generate the electricity. So we can see this figure where we have electric power generating systems. So there is a turbine and there is a generator. So turbine is coupled with the generator, and there is a frequency sensor. This sensor senses the change in the frequency, and there is a load frequency control mechanism. So this frequency is sent to this lower frequency control mechanism. It also takes the signal from the transmission line or tie line. Then it will uh, give a signal to the valve control mechanism. So this valve control mechanism is used to control the steam. Uh, so if this valve control mechanism controls the steam in the turbine, and in this way the speed of the turbine is regulated. And if the steam of the turbine is regulated, means the generator power is also regulated. So there is another loop. We will use a voltage sensor for this loop. It will sense the voltage, and there is a automatic voltage regulator mechanism. So this automatic voltage regulator mechanism, after sensing the voltage, will give the uh, DC current to the excitation system of the generator. Now the excitation system of the generator is available. Yes, Himanshu. Excitation system of generator is also available at the
ये थी वाली गई है
rotor.
ना ही है
Himanshu,
हिमांशु
please mute yourself.
तब आ ही खाए
हिमांशु
Himanshu
अरे यार
Kumar.
दिया छोड़ा करे ना ये तो बनावे लगे
Himanshu Kumar. Yes. So the excitation system at the rotor or the field at the rotor, the current in the field at the rotor is controlled by this AVR, automatic voltage regulator. So they actually in power system at the generation side there are two loops. One loop is used to control the frequency or generation, and other loop is used to control the voltage. So these loops are very essential for the control of frequency and voltage at the generation side. However, in the current scenario, we use various methods to control the voltage and frequency at the load side also. We use various capacitor panels at the load side to control the voltage, and we have various distribution generations at the load side to control the frequency. We also use load shedding mechanism to control the frequency. If we check that the frequency is less, then we can uh, use this load shedding mechanism to switch off the light of some feeders. So in this way, we can control frequency at the load side, voltage at the load side, and we can also control the frequency and voltage at the generation side. So this is the generation side. For control of the frequency, we will use this load frequency control loop, and to control the voltage by controlling the excitation current at the rotor of the alternator, we will use this AVR, automatic voltage regulator. So these are very essentials. So these loops are responsible to make the voltage and frequency constant or in a stipulated or scheduled limits. If these limits are violated, then there will be a condition of voltage collapse, and there may be a condition of frequency collapse. So to maintain the security of the system or stability of the system, so these two loops are very essential. Now this is the figure of LFC loop, and we can see that there is a generator and there is a turbine, and in turbine there is a steam. Steam comes in the turbine through a valve. So this valve actually should be regulated. So the regulation of this valve is very essential. So if this valve is regulated effectively, the steam entrance in the turbine can be maintained effectively, then we can regulate the frequency very effectively. So here there is a frequency sensors. So we will use frequency sensor to measure the frequency, and there is a frequency setup point in India. This is 50 Hertz. So what is the current frequency at the lines, and what is the schedule? What is the frequency set point? They are compared with each other, and if there is a deviation between the frequency, then these signals are sent to control the valve of the steam entrance to the. So the upper dotted lines indicate that if there is a deviation in the frequency takes place, this upper dotted line goes to a speed regulator. So this speed regulator is used to regulate this steam valve by using a hydraulic amplifier. So in hydraulic amplifier, there is a high pressure oil. This high pressure oil actually move this piston in downward direction or upward direction, and in this way this steam valve is regulated, is used to regulate the steam into the turbines. So it is a linkage mechanism. It is a linkage mechanism which is regulated by the speed of the regulator. Now there is another point that is termed as speed changer point. So this speed changer point actually is the set value. So this is responsible if we will change this the servo motor available here, the speed of the servo motor, if we will change effectively, then we can reduce the deviation in the frequency very effectively. So to regulate this speed changer or this set point, so actually we will use a controller. So here this is a integral controller. So this integral controller is used to regulate the position of the speed changer. So it is very important in the sense of this integral controller. So we will consider a free regulator mechanism. The system will be act as free regulator mechanism. Some stream will be regulated by the speed regulator, but the deviation in frequency will not be eliminated effectively with only speed regulator. So a integral controller is essential. Now this is a free governor action. Free governor actions means this integral controller is not used. Means by we are not changing the set point of the speed changer. This point is fixed. So here we can see that this is the speed changer point. So this point is fixed. There is no change with the change in the frequency using any integral controller. So we are only showing here 1 by R is the speed regulator, and this is speed governor, this is turbine, then generator. So if we will use this free governor action, means we are not using any control action. In that case, if there is a load taken place, then frequency will deviate. Means so at y axis there is a delta f. Delta f means change in frequency. At x axis there is time. So we can see that the change in frequency, which was originated from zero value and goes to in the lower side, and it settle at around minus 0.03 hertz. So if this error delta f is an error, this error actually should be zero. So this error is available. We can see that with the free governor action, when we applied a load, the frequency deviate, this error goes to in my negative side up to minus 0.045, and due to this governor actions, this deviation in frequency, which was 0.045, settle at minus 0.0, means there is some improvement in the frequency, but this error is not zero in the presence of free governor action. So we should require this integral control action. So in this slide, integral control action is used, means we have added a controller here, integral controller here. The system is same. In this case, we have used the integral controller. We can say that now this deviation in frequency in steady states settle at zero position, means the error in frequency is now equal to zero. So this error in frequency is equal to zero due to the presence of this integral controller. So in India, some years back, to control the frequency, we were using this free governor action only and the load shedding. Okay, so to control the frequency, we were using this free governor action and the load shedding. So now we have implemented this load frequency control in India at various generators. So we can now we are using this control action, and we can in a less time we can reduce this error to zero. So actually we are currently using this load frequency control in India. Now this integral controller can be optimized by using some conventional or advanced methods. So because if we will optimize this, the response of the frequency will improve. So we can use advanced control actions. In this slide, this is a cascade fuzzy fractional order PI and FOPID controller. So in cascade control, there are two controllers which are connected in cascade. So in the inner loop there is FOPID controller, and in the outer loop there is a fuzzy fractional order PI controller. So it is an advanced controller which is used. So this is the figure of this cascade control. You can see that this is a fuzzy controller, FLC fuzzy logic controller. Then there is a fractional order PI controller connected in cascade. Then there is a FOPID controller that is also connected in cascade. All three controllers are connected in cascade. So it is the advanced control action. So the used membership functions are shown here, and in fuzzy logic controllers, actually we used fuzzy. We use the signal. We fuzzified the signals. We can see that this is a plant. Then we will use sensors, and the data of the plant or output of the plant will go to the at summer. Then there will be some set value. We will compare these two values and we will get an error. So this error, this is a crisp error. So we have to fuzzify this error. So we will use fuzzification. Then we will use some fuzzy rules. So this table indicates that these are the fuzzy rules. So we have used fuzzy sets having linguistic variables. So we have linguistic variables like large negative, medium negative, small negative, then zero, small positive, medium positive, large positive. So we have these rule base for, here is written some ACE and ACE derivative. So ACE is termed as area control error, and AC derivative area control error derivative. So in this case, this area control AC E is nothing but it is delta F. So it is delta F and delta F derivative. So using this, we will make rules. So here are 7 membership functions. So we will make 7 into 7, 49 rules. And these rules will be fired in the fuzzy inference system. And we will get a fuzzy linguistic output. And after this fuzzy output, we will use defuzzification method, and then we will get a crisp variable, and this crisp variable is used to control the plant. So this is the advanced control. So in this table, we have given the controller parameters like Kp, Ki, lambda, Kp1, Ki1, lambda1, Kd, mu. So these are the parameters of fractional order controller, FOPI or FOPID controller. So in this system, there is a controller termed as FPI, fuzzy proportional integral controller. So its values are given here. Then fuzzy fractional order PI, these parameters are also given here. Then this advanced control, that is termed as cascade fuzzy fractional order PI FOPID controller. So these parameters of this controller, using a optimization technique, these values are given here. Now the results of the advanced control action are shown here. We can see that this is the red figure, dotted figure. So it is the result of GAPID controller. Then there is a green result GAFOPID controller. Then there is a imperative commutation algorithm, competitive algorithm. So it's this imperative competitive algorithm is used to optimize the FPI, proportional integral controller parameters. Then the same algorithm is used to optimize the fuzzy fraction order PI controller. The same algorithm is used to optimize this cascade controller. So we can see that results of this advanced controller, we can see that when we will apply the load, this black result, the deviation in the lower side is very less compared to others, and it also settle in very less time at the value of 0. So these results or the frequency control can be improved by using some advanced controllers. So the second result is given in the B part. The second result is the power output. So actually the value settles at 0.01 per unit megawatt value because we have applied the disturbance or load demand which is equal to 0.01, and we can see that by using this advanced control, the generation due to this advanced control settles at the desired value of 0.01 per unit megawatt in the minimum time and with very less oscillations or no oscillations. So in this way we can improve the response of the results are taken from the published paper. Now this system was the isolated system. This system was the isolated system. Means it is not connected with other generators. So there may be interconnected power system. As we have discussed in the beginning, all our grids are interconnected now. So there may be a power company A, power company B, C or D. They are actually interconnected with each other, just like our 5 regions. And tie lines are used to transmit power from one company to other company or one control area to other control area. So to study this, we use control area. Control area means the generators which are connected with each other with strong tie lines. Strong tie lines means the distance of the transmission lines are very less. So in a control area, all generators are connected with the strong tie lines, and it is assumed that they will speed up or speed down as per the load demand in unison. Unison means they speed up and with each other. So such type of generators which are connected with the strong tie lines, they are considered a control area, and other power company or other control area which is situated around at a longer length, we can consider that the other area is connected with the other area by weak tie lines. So so it is an integral control action. We have taken an example of two control areas interconnected. So this is one area and this is other area. They are interconnected with each other. So we have taken an example of two areas which are connected with each other, and we have used integral controller. So the same figure is given here. We can see that this is a secondary controller or integral controller, and the upper is thermal unit and lower area 2, there is thermal unit. Thermal unit means there is a governor, there is a turbine, and there is a power system. And these two power systems are interconnected by a tie line. The transformation of tie line is given by T1 to by S. So, and this 1 by R actually it is indicating the speed governor, and this B it is indicating the frequency bias. So we can see that this is ACE. ACE means area control error. So area controller, we can see that it is the sum of two signals. One signal is tie line signal and other signal is frequency signals. Means we can see that this AC1 is nothing but delta F1B plus delta P-tie. In the same manner, this AC2 will be nothing but delta F2B plus delta P-tie. So this AC or this area control error will go to the this secondary controller or integral controller, and it will give a reference value. And on this, if we will change this reference value very quickly or very effectively, we can reduce the error in the frequency in less time very efficiently. So for this two-area system, there is another controller here is taken, that is the fuzzy PID controller. So it is a fuzzy controller and it is a PID controller. So it is a fuzzy PID controllers. So these are members functions taken for this system, and these are the fuzzy rule base for the system. And the controller optimized values of the controller, they are obtained by using BFOA, bacterial foraging optimization algorithm. So these values are given here for BFOA FPI fuzzy proportional integral, and this BFOA FPID means fuzzy PID. So we can see that the response of the frequency, change in frequency for area on delta F1, it is shown in this figure, and we can see that the result, which is shown by BFOA FPID, will have less, very less or least undershoot, and it take very less time to settle at 0. Means it is highly effective controller compared to other controllers. Other controllers have more undershoots, and they also have overshoots. They also have oscillations, and they also have more settling time to settle at the desired value of 0. Means when we will apply a load of about 10%, then frequency will go down, and because we are using supplementary controller or frequency load frequency controller, so it will recover very quickly and frequency error becomes 0. So in this figure, the left hand side figure is delta F2, means it is the response of frequency of area 2, and this response in the left hand side belongs to delta PTI, tie line power. So we can say that the response due to this BFOA FPID is very, very good, and it significantly improve the frequency response compared to other. So these responses are also taken from the paper published in Soft Computing Journal. Now come to the competitive environment, means restructured power systems. So actually in India we are actually moving from the traditional system to the restructured systems. In previous times there was one company which was generating power, which was transmitting power, and which was distributing power to the consumers. So, but in current scenario, there are various GENCO, Genco, these are Genco generation companies. There are various generation companies. We also know that there are various private generation companies, just like Sterlite, Toronto, Adani Power, Reliance Power. So they have their generators to generate power, and there are various discoms distribution companies, just like in Haryana there are Dakshin Vidyut Vitran Bijli Company, Uttar Vidyut. So there in Delhi there are BSES, Rajdhani, BSES, Yamuna, so and Transmission, Tata Distribution Company. So these are discoms. These are distribution companies. So in a restructured system, these distribution companies have autonomy to make contract or to purchase power from the generation companies whose rates are less. So to make the power economical to the consumers, so we have this restructured power system creates a competition among the generation company to sell their power at economical rates. So these discoms have now contracts with the Gencos. So this facility was not available in the previous traditional method of power transmission, distribution, and generation. So now this restructured system is very efficient for the point of consumers. So in if these distribution companies make contracts with the generation companies, there is a independent system operator. So this independent system operator is very crucial. Its role is very crucial because power comes over the transmission lines. So discoms make contracts with Gencos, but the power will come over the transmission lines. So these ISOs or independent system operators allow these contracts. Without their permission, contracts cannot be made. So their permission is very essential. So their permission is essential to maintain the security of the system. Okay, so to maintain the system secure, so they will check the power transfer capability of the transmission line, and so for this there is a approval. Their approval is very important. So in the below figure, we have used area 1, which had DISCO 1, DISCO 2, GENCO 1, GENCO 2, and there is another TRANSCO 1, transmission company. Okay, and in area 2, there is also 2 GENCOs. We think that there are 2 GENCOs, GENCO 3, GENCO 4, and DISCO 3, DISCO 4. Means we will simulate this system where in area 1 there are 2 GENCOs and 2 DISCOs. In area 2 there are 2 GENCOs and 2 DISCOs, and their names are in area 1 GENCO 1, GENCO 2, and DISCO 1, DISCO 2. In area 2 their names are GENCO 3, GENCO 4, and DISCO 3, DISCO 4. Also there are in area 1 there is Transco, transmission company, and in area 2 there is also a transmission company to transmit these powers over the transmission lines. And this in middle of these there is ISO. So approval of this ISO is crucial, or it is mandatory to avoid any security problem in the transmission system. Now, in restructured system, so actually this DPM, it is termed as DISCO partition matrix. It is actually used. So it make visualization of the contracts easier. So its use is very, very essential. So the DPM, it has a number of rows and columns. So the number of columns actually denotes the number of distribution companies, and the number of rows actually denotes the number of generation companies. Means you can see the Genco 1, Genco 2, Genco M. In the same manner, regarding column, there will be Disco 1, Disco 2, and Disco M. And this is termed as CPF. It is termed as contract participation factor. So the elements of this DPM are CPFs, contract participation factor. So these are the elements of this DPM. We can see that the first row we can state that CPF11, then we will state that CPF12 and CPF1. Means CPF11 means it is the first first Genco and first Disco. CPF12 means it is first Genco, second Disco. So in the first column we can say that CPF11, then CPF21, then up to CPF1. Means the first Disco, and there will be second Genco and MF Genco. So it is very, very important to decide these CPF's value. So CPF, we can say that CPF, what do you mean by CPF IJ? Means it is a fraction of total load contracted by a Disco J. Means column towards Genco I means row. So CPF IJ means I means Genco, or J means Disco. So there may be different types of contracts or power transactions which may take place between Discos and Gencos. It is not Transco, but it is Gencos. So there may be a pool-co based transaction, then there may be a bilateral based transaction, then there may be a pool-co plus bilateral transaction, then contract violation based transaction. In pool-co based transaction, actually in pool-co based transaction, it takes place in one area. Means it is a transaction between the Discos and Gencos situated in a single area. And second number is bilateral based transaction. So these transactions are taken place between the Discos of one area to the Gencos of other area, and Gencos of the second area to the Gencos of the first area. So these are bilateral transactions. So there may be another transaction, pool-co plus bilateral, means there may be contracts between the same area as well as in other areas. Means Disco have transaction or contracts with the Gencos of its own area, and the same Disco also has contracts with the Gencos of the other area. And there may be another transaction, contract violation based transaction. Actually, when there is a transaction takes place, so there is a transaction of power contracts made between these two companies, Disco and Genco. So they mutually agreed the amount of power taken by the Disco. Sometimes Disco overdraw the power. So that is termed as the contract violation based transaction. So if that Disco will overdraw the power, then that will affect the frequency or system stability. So in that case, the rates of the power will be different as per the. So as discussed before, we have used two area system. The Disco 1, Disco 2, Genco 1, Genco 2 in area 1. Disco 3, Disco 4, Genco 3, Genco 4. These companies are situated in area 2. and it is given here DPM, disco participation matrix. So we can see that the columns are designed for the disco 1, disco 2, disco 3, disco 4, and rows are designed for GENCO 1, GENCO 2, GENCO 3, GENCO 4. Okay, so disco 1 may have contracts with GENCO 1, GENCO 2, GENCO 3, GENCO 4. So the total power contracted by disco 1 may be with the different GENCOs. So in this DPM, the sum of the any one column will be equal to 1. So this CPF may be let 0.2, then 0.2, then 0.2, so 0.2, 0.2, 0.2, 0.6, and last must be 0.4. So the sum of the column must be equal to 1. 1 means the total power of the disco 1. So another term is APF. APF means area control error participation factor. So it will also used in this simulation. So this AC signal has to distributed among GENCOs of an area in proportion of their participation in load frequency control. So this AC APF will be used, and its value will be utilized in various calculations in the next slides. Now we have used this integral controller action. We have used two area system. The upper area is control area 1 and lower is the control area 2. In upper area 1, there is two thermal units used. Also in the lower area, there is two thermal units are used. And we have thermal units means two GENCOs in area 1, two GENCOs in area 2. And the type of GENCOs are thermal. And this is the integral controller 1, integral controller 2. Now you can see here APF 11. So this is the area partition factor. Is so APF 11, APF 12. So the addition of APF 11 and APF 12, this should also be equal to 1. In the same manner, there is APF 21 and APF 22. The addition of APF 21 and APF 22, this should also be equal to 1, because it indicates the total control area which is divided as per the APF IJ. Now the load, it is the disturbance indicated here. So we can see that there is delta PL1 LOC and delta PUC1. So PL1 LOC means local load and PUC means uncontracted load. So total disturbance will be, or total load demand will be categorized as local load and uncontracted load. And it is the tie line, and we can see that the tie line, there are two signals available here: tie line actual, delta PTI actual, and delta PTI scheduled. So the delta PTI scheduled, there is a specific formula to find out delta PTI scheduled. So it has a specific formula. We will see it. So delta PTI scheduled will be calculated as per the power exported to other area minus power imported to the first area. So we will check. Now we can see here that these are the, actually the lower portion denotes the DPM. So here we can see that in delta PTI scheduled, E plus F minus C plus D. So this is the formula which we will discuss here. So we actually have taken case 1 where pull go based transaction is taken. Here we have taken APF 11 APF12, APF21, APF22. Their values is equal to 0.5. And load change in area 1. We have taken load change in area 1 only, means load is demanded by disco 1 and disco 2 only. Means the load demanded by disco 1 is denoted by delta PL1, and load demanded by disco 2, it is denoted by delta P2, and it's equal to 0.04. And the load demanded by disco 3 and disco 4, it is indicated by delta PL3, delta PL4, and its value is given to 0, because we have assumed that the load demanded by disco 1 and disco 2 only. Now this is the DPM considered here. We can see here that in the first column of the DPM, the value is 0.5. So the addition of these two values will be equal to 1. In the second column, there is also 0.5. Its addition of the column value will be equal to 1. So, and here we have written delta PL1, PL2, PL3, PL4. Actually, these are the disco 1 to disco 4. And by using this DPM and these discos, we will find the generation done by the generation company 1, generation company 2, 3 and 4. So how we can find this power generated by Genco 1, Genco 2 and Genco 4? So this is a formula. So here we can see that the power generated by Genco 1 is given by delta Pg11, and power of Genco 2 delta Pg12, and by generator it is also shown here. This is power generated by Genco 1 delta Pg11, Genco 2 delta Pg12, Genco 3 delta Pg21 and Genco 4 delta Pg22. So these powers are actually find out by using this DPM. So we will find Pg11 by using this formula, means CPF11 into PL1 plus CPF12 into PL2 plus CPF13 PL3 plus CPF14 PL4. So first row will be multiplied with this delta PL1, PL2, PL3. Means these are disco. So from here, if we will feed these values here, so we will find that the generated power, steady state value of the generated power from Genco 1 will be equal to 0.04 per unit megawatt. In the second case, the power generated by the Genco 2 means delta Pg12. So again we will use the same formula, CPF11 PL1 CPF12. So from here we will find that in this case also the power generated by the Genco 2 is 0.04, and we can also check that the power generated by the Genco 3 is equal to 0 megawatt, and Genco 4 delta Pg22 is 0 megawatt, because we have taken Poolco based transaction, means there is a transaction taken place between the disco 1, disco 2 and Genco 1, Genco 2. Means when there is no transaction, power will be 0. So here we will see the results. So these are the results. We can see that using integral controller, the delta F1 means it is the F1 response, it settles at 0 value, F2 it also settles at 0 value, and this is delta P tie actual, its value also settles at 0, and there is another term that is delta p error. Its value also settle at 0. Now come to the generation from the GENCO 1. You can see that the GENCO 1 generation is 0.04. And you can also see that generation from the GENCO 2 delta PG12 it is also equal to 0.04. And generation from GENCO 3 it is equal to 0. Also generation from GENCO 4 it is also 0. And these are the values, means the simulations results confirm these values. And now it is p actual. This signal is p actual, and this is p scheduled, and this is p error. Means this error it is the resultant of these two values. Means we will minus the signal data p actual and p scheduled. So p scheduled signal will be minus from the p actual. So in this way we will get an error. So here we have shown these signals, means data p actual, then error. So now how we will find this p scheduled signal? So already said that there is a formula to get to find out this p scheduled. So this is power export from first area minus power import to the first area. So this formula is used. Now here power exports means it is written here E plus F. Power import means C plus D. Means we can say that demand of discos in area 2 from GENCOs in area 1. So it is exports, means GENCOs of area 1 are generating power and transmitting to the discos of area 2. And import means demand of discos in area 1 from the GENCOs of area 2. Means GENCOs of area 2 is generating power and transmitting this power to the area 1. Now this p schedule can be find out or can be formulated by this formula, means P export. P export means GENCO of area 1 and discos of area 2. So we can use this formula, means CPF 13 plus CPF 23 delta PL3 plus CPF 14 plus CPF 24 delta PL4. Delta PL4 means it is a disco of area 2. Delta PL3 it is the disco of area 2. And CPF 13 means GENCO 1 disco 3. CPF 23 means GENCO 2 disco 3. CPF 14 means GENCO 1 disco 4. CPF 24 means GENCO 2 disco 4 means GENCO 1 and GENCO 2. They are generating power. And disco 3 and disco 4 they are taking power from GENCO 1 and GENCO. Means disco 3 and disco 4 they are situated in area 2, and GENCO 1 and GENCO 2 they are situated in area 1. So means power is exporting from area 1 to area 2. In the second case, power import means 3 1. Shivangi, please mute. Shivangi, please mute your mic. Shivangi,
एमिटर से हम निकालते हैं, कलेक्टर से एमिटर से मतलब इनसाइड निकालते हैं, इनसाइड और आउटसाइड कैसे निकालोगे?
शिवांगी,
हाँ बनाओ, क्या बनाओ, तो फिर बनाओ, ये कैसे होगा? बना
हेलो
तुम्हें कौन है पता भी है तुमको?
हेलो
सब सिक्योरिटी रिपोर्ट चुके हो?
आर यू हेयरिंग मी हेलो
कलेक्टर बेस एडिटर
शिवांगी
हेलो
मुझसे पूछ के बता रहे हो?
हेलो
हेलो हेलो
यस यस
इधर की बात है।
यस आर यू हेयरिंग मी करेक्टली ओके ओके सो
यस
okay okay so these are the results when power when pool co based transaction takes place. So this value of delta p time schedule actually is calculated from this formula, and in this case because we are using pool co based transactions, we are not exporting power or importing power from the other area, so this p time scheduled will be equal to 0. So because of this, the p time actual and p time error, they are equal to 0. Now, in the second case, we are using bilateral based transactions, means the GenCos of one area will make transaction with the dispose of other area. Here, we think that the dispose of both areas, means PL1, 2, 3 and 4, they have a demand of 0.04 per unit with the GenCos. Okay. And we also have indicated that APF, area partition factor values are 0.75 and for area 1 APF11 and APF12 0.25. We can see that the addition of these two values is equal to 1, and the values of area 2 APF21 and 22, they are equal to 0.5. So this DPM is taken for this case, bilateral case, and for after using this p-tie scheduled formula, we find that the p-tie scheduled value is minus 0.02. Okay, so from this formula its value is minus 0.02. Okay, now we will also find the power generated from GenCo 1, 2 and 3. We will use the same formula already we have used. So we find that the GenCo 1 output is 0.042 per unit, GenCo 2 output is 0.018, then GenCo 3 0.078, GenCo 4 0.022. Now these are the results. We find out that in the same manner, when we will apply a load, the frequency will settle 0 because we are using a controller of area 1, area 2, both frequency settle at 0, desired value is 0, and we say that we also check that the delta p tie actual value is minus 0.02, and we also find out that delta p tie scheduled value is also minus 0.02. Okay, so scheduled value and actual value both are equal, means the tie line error will be equal to 0. So the tie line error is equal to 0. Now come to the power generated from GenCo 1. So its value is 0.042. So we can see that its value, the power generated from GenCo 1 is shown here. Its value is also 0.042. And power generated from GenCo 2, its value is 0.018. And we can verify this value from this figure. And GenCo 3 power is 0.078 and its value is 0.078. Also, the power generated from the GenCo 4 is 0.022 and it is also here. So we can find that by using a controller and same formulation, we can visualize the contracts between the DISCOs and GenCos, and we are getting the correct results. And if we will take another contract, means contract violation, and we will consider case 2 with the modification that DISCO 1 demands 0.04 per unit access power. Okay, so in area 1, the signal which was shown here, delta PUC1, so it is uncontracted power, so its value will become equal to 0.04. Now delta PUC2 will be 0 because we have imagined that the power contact takes place in area 1 only. So the total load in area 1, so there was already load of the disco 1 and then disco 2 and this unprotected load. So 0.04 plus 0.04 plus 0.04. So load in the area 1 will be 0.12 per unit. Similarly, total load in area 2, because delta PUC1 unprotected load is 0, so that will be same, means PL3 plus delta PL4 0.08. Now this APF, area ACE partition factor, will be used here. So already we have checked that the delta PG1 in the previous case was 0.042. Now this is the delta PUC1 will be multiplied with APF11. So APF11 value is 0.75 and delta PUC1 0.04. So its value will become 0.072. And in the same manner, we will find the updated power generated from the GENCO 2. Actually, if there is a unprotected power takes place in area, then that unprotected power will be generated by the same area itself, not by the second area. So delta PG12 was 0.018. Now this unprotected power will be 0.25 into 0.0, so it will become 0.028. And delta PG23 means GENCO 3 and GENCO 4 powers will be same, 0.078 and 0.022. So these values are same, 0.078, 0.022. But these values have been increased. 0.042 and 0.018, they have increased to 0.072 and 0.028. Now we will check the results. We can check the results that case 1, case 2 and case 3 contract violation. We can, when there is a contract violation takes place, we see that there is a large deviation in the frequency signal in area 1 to area 1 and to both areas. And we can also see that the tie line actual power is same, but there are more oscillations in the case when there is a contract violation takes place. In the same manner, the same oscillations are available in tie line error. Now we can also see that in case 2, which was power was 0.042, now it increased to 0.078. So this red color is indicated that in contract violation power generation has been increased in area 1. In the same manner, power generation from GENCO 2, it is also increased. Its value is 0.028, which was 0.018. It is 0.018, it is 0.028. But we can see that the power generation from GENCO 3 and GENCO 4, they are same. However, there are more oscillations if contact violation conditions takes place. So this was a introduction to various limitations or opportunities in power system operation control relating to the frequency control aspects. So if you have any question, you can ask, please.
Participant, if you have any question, please ask.
Yes, sir.
If you have any question, please ask. Okay, no one has any questions.
Okay, sir.
ओके सर, थैंक यू सो मच सर, आपने इतना टाइम दिया उसके लिए बहुत बहुत
Okay, thank you very much, sir.
थैंक यू सर.